All right, physics students, today you were asked to do numbers 1, 3, and 4, talking about general launch angle projectiles. And so I'm going to do number 1, and you can kind of see how this goes. So number 1 says that in a scene in an action movie, a stuntman jumps from the top of one building to the top of another building 4 meters away. After a running start, he leaps at a velocity of 5 meters per second at an angle of 15 degrees with respect to the flat roof. Will he make it to the other roof, which is 2.5 meters lower than the building he jumps from? All right, so what's going on here? Let's draw a picture first. The first thing is there's this building, and the criminal is running away. Okay, and then there's another building, and it says that this building is 4 meters away. So this distance is 4 meters. Okay. Now it says that the height of this building is 2.5 meters higher than this building. So he's going to drop, should he make it, 2.5 meters. All right, so then it says that when he jumps at an angle of 15 degrees, and it says that his initial velocity, V naught, is 5 meters per second. Okay, so the question is he going to make it across? Will he drop less than 2.5 meters after he's traveled 4 meters. So there are actually two different ways that we can go about this problem. So, but the first thing I want to do is write down everything I know. So I'm going to write down my variable tables: Vx, V naught x, Ax, delta x, T, Vy, V naught y, Ay, delta y. All right, now, if this was a zero launch angle problem, there would be some extra things that I know. Like I would know that the initial y velocity is 0, but in this case it's not. In this case, if we pull out that velocity vector, v naught, we see that it is made of two components. I have v naught x, and there's a vertical component now, v naught y. And v naught x is equal to v naught times the cosine of theta, and in this case theta is 15 degrees, and v naught y is v naught times the sine of theta. All right, so let me figure out what those things are. So for the first one, V naught x is going to be 15 times the cosine, I'm sorry, not 15, 5 times the cosine of 15. And up here for V naught y, it's going to be 5 times the sine of 15. So 5 cosine 15 equals 4.8 meters per second. That's V naught x. And V naught y is going to be 5 sine 15. That's going to be 1.29. All right, so I can plug those in to my chart here: 1.29 meters per second for V naught y, and 4.8 meters per second for V naught x. Now remember, after he leaves this building, there is nothing pushing him forward anymore. He's going forward because he was already going forward. There's no force, therefore no acceleration, which means that V naught x and Vx are the same. I'm going to hold off on delta x here for a second. I know that in the y direction, the acceleration is the acceleration due to gravity, which is negative 9.8 meters per second squared. I don't know what his final velocity is, and I'm also going to hold off on delta y. The reason I'm holding off on delta x and delta y is this is where we come to a place on how we want to do the problem. I can say how far would he drop if he goes 4 meters, and then delta y would be my unknown. And if it's less than 2.5, then he makes it. Or I could say he's going to drop 2.5 meters. If his delta x ends up being more than 4, then he makes it. All right. So let's do it this way, where we know delta x and we're going to try to find what delta y equals. All right, so in order to find delta y, I look at my variables. I have v naught y, ay, and delta y, and I look at my chart here, v naught a delta y, but I don't have time and I don't have vy. So I can't solve this. So again, like my zero launch problems, I'm going to have to solve for time. And I'm going to have to solve for time from my x variables here. All right, so what do I know in the x direction? I know v naught x, ax, delta x, and t. And so like so many of these other problems, I can just use equation number 3. Delta x equals v naught t plus 1/2 at squared. So let me write that down. Delta x equals v naught x t plus 1/2 ax t squared. All right, and I want to solve for time. Ax is 0, so that whole term goes away. Let's divide both sides by v naught x. And that's going to be 4 meters divided by 4.8 meters per second. So 4 divided by 4.8 equals 0.83 seconds. All right, so that's my time, and that's going to shoot up to here. Now I can look at time as being part of my y variables. And what do I have? I have exactly the same set of variables, just in the y direction. So I'm going to use exactly the same equation I did before, only with y subscripts. So delta y equals v naught yt plus 1/2 ayt squared. Now, like I said, in zero launch problems, v naught y would have been 0, but it's not now because we're not leaving at 0 angle. So we found out what that is. So what I need to do now is I need to just plug everything in. I don't need to rearrange. So v naught y is 1.29 times my time of 0.83 plus 1/2 times ay, which is negative 9.8, times 0.83 seconds squared. Right, and so now we'll get the calculator out, and 1.29 times 0.83 plus 0.5 times negative 9.8 times 0.83 squared equals, and that's negative 2.3 meters. So, did he make it? Yes. He, at 4 meters, he still has only dropped 2.3 meters. He's right here. So he'll keep dropping and eventually land right there. And it's negative again because he's moving downward. All right, there you go.